A single teaspoon of neutron star material weighs more than a mountain. This cosmic forge is the violent birthplace of the heaviest elements in the universe, from the gold in a ring to the uranium powering our cities. By the end of this journey, you will understand the spectacular origin of the very atoms that make up our world. We will uncover how a stellar corpse can create new matter and trace the path of cosmic debris from a distant explosion to our planet. What does the story of our own existence reveal about the most powerful events in the cosmos? The life of a massive star is a constant battle against its own immense gravity. For millions of years, the outward push of nuclear fusion in its core holds the star up, preventing it from collapsing under its own weight. But this fight has a time limit. When the star finally exhausts its primary fuel, the balance of power shifts in an instant. The steady furnace at its heart sputters and dies. Without that outward pressure, there is nothing left to resist gravity's relentless pull. The star's core, which can be more massive than our entire sun, is no longer supported. It simply falls in on itself. This is not a gentle sinking. It is a catastrophic collapse where an object the size of a giant star is crushed down in a matter of seconds. The core plummets inward at speeds approaching a quarter of the speed of light. This sudden, violent implosion triggers a shock wave of unimaginable force that ripples outward, blasting the star's outer layers into the void in a supernova explosion. For a brief moment, this single star can outshine an entire galaxy. When the cosmic dust settles, the scattered remains of the star enrich the surrounding space with new elements. And at the very center of this chaos, where the core once was, a new object is born from the wreckage. All that immense mass is compressed into a sphere no wider than a city. This is the neutron star, a remnant so dense that a single sugar cube-sized piece of it would weigh as much as every person on Earth combined. The supernova is the spectacular funeral pyre, but the neutron star is the phoenix that rises from the ashes, a cosmic forge ready for its next act of creation. This city-sized sphere born from a star's death is a cosmic paradox. It contains more mass than our entire sun, yet it is compressed into an object you could theoretically drive across in under an hour. To understand how it forges elements, we must first grasp its extreme physics. Imagine taking every car, every building, and every person on our entire planet and crushing them down into a single sugar cube. That still falls short of the density inside a neutron star. The gravity here is so overwhelmingly powerful that it fundamentally rewrites the rules of matter. The atoms that make up our world, with their spacious electron clouds orbiting a tiny nucleus, cannot survive here. The immense pressure literally squeezes the atoms themselves, forcing the negatively charged electrons to crash into the positively charged protons. This cosmic merger cancels their charges, and they fuse into neutral particles called neutrons. The entire star becomes a vast, ultra-dense sea of these subatomic particles, which is how it earns its name. This neutron sea is not still. It is locked inside a crust 100 trillion times stronger than steel, a crystalline surface that can form mountains no more than a few centimeters high, yet which support the weight of entire Himalayas. The star spins at a dizzying rate, sometimes completing hundreds of rotations every single second, and its magnetic field is so potent that if one were placed as far away as our moon, it could erase the magnetic strip on every credit card on Earth. This is not a quiet, dead remnant. It is a furious, hyper-dense engine, a natural laboratory where conditions are so extreme they cannot be replicated anywhere else. And within this engine lies the secret to building the heaviest things in the universe. Look at the world around you, the device you are holding, the ground beneath your feet, even the air you breathe. All of it is made from elements cooked inside stars. For billions of years, stellar furnaces have been transmuting simple hydrogen and helium into the carbon, oxygen, and nitrogen that life is built upon. Yet this cosmic production line has a strict cutoff point. Inside a star's core, the process of nuclear fusion, which smashes lighter atoms together to make heavier ones, is a delicate balance. It releases tremendous energy, which in turn keeps the star shining and stable. This works perfectly until the star begins creating iron. Iron is different. Fusing iron atoms does not release energy, it consumes it. It acts like a fire that, instead of giving off heat, starts sucking it from the room. The moment a star's core fills with iron, the central furnace sputters out. The star has reached the end of the line for its peaceful, energy-producing life. So if stars cannot make anything heavier than iron, where did all the gold, silver, and platinum come from? Where did the uranium that powers nuclear reactors originate? The universe was left with a puzzle. Building these heavy elements requires an enormous input of energy, a violent process known as nucleosynthesis. For decades, the source of this cosmic forge was a profound mystery. The answer, it turns out, was not found in the quiet glow of living stars, but in the chaotic aftermath of their catastrophic deaths. For decades, the mystery of our universe's heaviest atoms seemed to have no adequate solution. Then, astronomers pieced together the answer, discovering that nature uses two distinct cosmic recipes. The first is a slow, patient method that unfolds over centuries inside the calm interiors of giant red stars. Known as the slow neutron-capture process, or S process, it steadily adds neutrons one by one, like a meticulous chef carefully assembling a complex dish. This process creates a portion of the heavier elements, but it is too gentle, too orderly to forge the very richest prizes. For elements like gold, platinum, and uranium, the universe requires something far more violent and chaotic. It needs the rapid neutron capture process, or R process. Think of this as a frantic, high-stakes race against time. In this scenario, an atomic nucleus is bombarded by an overwhelming flood of free neutrons. It must capture dozens of these neutrons in the blink of an eye, far faster than they can naturally decay. This rapid assembly builds up an incredibly heavy, unstable nucleus, which then settles down through radioactive decay, transforming itself into the stable, precious elements we know. This entire breathtaking sequence can happen in just a fraction of a second, but this cosmic sprint demands a very specific and extreme environment. It requires a place flooded with an almost unimaginable number of free neutrons. This single, critical requirement narrows down the possible locations in the entire cosmos to just a handful of the most violent events known to exist. This frantic race against time, the R process, is one of the universe's most dramatic transformations. Visualize a single atomic nucleus like a tiny seed, suddenly caught in a hurricane of free neutrons. There is no time for careful assembly. In less than 2 seconds, this nucleus is violently slammed with dozens upon dozens of neutrons, building it into an impossibly heavy and unstable form. It's a cosmic version of trying to build a house by having an entire lumberyard dropped onto the foundation all at once. This new, bloated nucleus is so rich in neutrons that it cannot hold itself together for long. It immediately begins to settle, undergoing a series of radioactive decays. Inside its core, neutrons relentlessly transform into protons, shifting the very identity of the element. This rapid decay carves the unstable, neutron-heavy blob into a final, stable, and precious element. The gold in a wedding band or the platinum in a catalytic converter was forged in this precise, high-stakes sequence. But this entire breathtaking event hinges on one non-negotiable requirement: an environment flooded with an almost unimaginable number of free neutrons. For decades, scientists knew the recipe but could not find the kitchen. They needed to locate a cosmic pressure cooker of epic proportions, a place where the very laws of physics are pushed to the breaking point. For years, the cosmic kitchen for the R process remained one of astronomy's greatest unsolved cases. Supernova were the obvious first suspects. They had the energy, the violence, and were known to be rich in neutrons. But the evidence never quite fit. When scientists ran sophisticated computer simulations of a typical star collapsing into a supernova, the results were disappointing. These models often failed to generate the intense, sustained neutron flood needed to create the vast amounts of gold and other heavy elements we see scattered throughout our galaxy. The supernova, for all its spectacular power, seemed to be missing a key ingredient. The scientific community was left with a glaring contradiction. The heavy elements were undeniably here, woven into the fabric of our solar system and our very bodies. Yet the primary suspect, the supernova, could not reliably account for their creation. This meant something else, something even more potent and rare, was operating in the dark corners of the cosmos. The hunt intensified for a more powerful, more neutron-rich engine. The mystery persisted for decades, a frustrating gap in our understanding of cosmic origins. Then, in 2017, everything changed. Astronomers witnessed an event so cataclysmic that it did not just release light, it sent ripples through the fabric of spacetime itself. This monumental observation finally provided the smoking gun, pointing decisively to a location even more extreme than a solitary supernova, a place where the ultimate cosmic forges, neutron stars, take center stage in a final, destructive dance. The collision sent a shudder through the cosmos, a ripple in spacetime detected by observatories here on Earth. In the autumn of 2017, a signal arrived not as light, but as a literal stretching and squeezing of the universe's fabric. For the first time, humanity felt the gravitational waves from two neutron stars spiraling into a final, fatal embrace. Within moments of this cosmic tremor, observatories around the world and in space swiveled to look, and they saw it, a brilliant flash of light unlike any supernova. This was a kilonova. For about 2 weeks, this event blazed with the energy of a billion suns, a short, spectacular fireworks show in a distant galaxy. The light itself told the story. As astronomers analyzed its color and evolution, they saw the unmistakable fingerprints of exotic, heavy elements. The glow was produced by the radioactive decay of freshly forged gold, platinum, and other rare earth elements, all created in that single, cataclysmic merger. A kilonova is the radioactive afterglow of a cosmic alchemy experiment on an unimaginable scale. When two neutron stars collide, they do not simply explode. They tear each other apart, ejecting massive clouds of their ultra-dense material into the surrounding space. This ejected material is a superfluid of free neutrons, the perfect environment for the rapid neutron capture process. In the chaotic swirl of the collision, atomic nuclei are bombarded with that unimaginable flood of neutrons, building the heaviest elements in the universe in a matter of seconds. The brilliant, colorful light of the kilonova is the direct evidence of this creation, the glow of these new, unstable atoms settling down and announcing their birth to the cosmos. That one observation in 2017 solved a decades-old mystery. It confirmed that the violent mergers of neutron stars are a primary cosmic factory for the universe's gold, platinum, and uranium. The kilonova was the missing piece of the puzzle, the definitive proof of where nature's most extreme element-building process takes place. The final spiral of two neutron stars is a dance of pure destruction. They begin by circling each other hundreds of times per second, their orbital embrace tightening with every pass. As they draw closer, the gravitational forces at play become so immense they can no longer hold their shapes. Each star begins to strip material from the other, stretching them into long, swirling tails of ultra-dense matter. This is not a clean impact but a violent shredding. When they finally collide, the event releases more energy in a single burst than our Sun will emit over its entire 10 billion-year lifetime. The outcome of this cosmic crash is twofold. At the very center, the combined mass often collapses instantly to form a black hole, a gravitational sinkhole from which nothing escapes. But it is the material flung outward from this cataclysm that holds the true prize. These are not gentle plumes of gas. They are jets of neutron-rich matter ejected at nearly the speed of light, a superfluid of subatomic particles racing into the void. This expanding cloud of debris, known as the ejecta, is the ultimate cosmic crucible. It is a place of almost unbelievable extremes, searingly hot and so dense that it is overflowing with the one ingredient the Are process desperately needs: free neutrons. Here, any stray atomic nucleus, a fragment of iron or carbon caught in the flow, is instantly subjected to a neutron hurricane. It is a blizzard of subatomic building blocks, and in this chaos, the heaviest elements in the universe are assembled in a heartbeat. The gold that now sits in a vault, the platinum in a laboratory, and the uranium deep within the Earth were all once part of this furious, expanding cloud, forged in a single, spectacular flash before our solar system even existed. That crystalline crust, forged under pressures 100 trillion times greater than Earth's atmosphere, becomes the ultimate cosmic quarry. Its structure is unlike anything we know, a rigid lattice of atomic nuclei, mostly iron, all swimming in a superfluid ocean of free neutrons. This is not a static shell. It is a reservoir of potential, a stockpile of the exact ingredients needed for cosmic alchemy. When two neutron stars tear each other apart in their final dance, their crusts do not simply crack. They are violently shredded. Immense tidal forces rip entire mountains of this ultra-dense material right off the surface, hurling them outward at incredible speeds. Once ejected into the near vacuum of space, these chunks of star crust experience a sudden and dramatic change. The unimaginable pressure that once held them together vanishes. It is like taking a deep frozen object and suddenly tossing it into a furnace. The crystalline structure instantly shatters, the atomic nuclei are freed, and most importantly, the sea of neutrons that was trapped within the lattice is released in a colossal burst. This creates the perfect storm for the Are process, a cloud of debris so rich in neutrons that it is essentially a soup of subatomic building blocks. Without this specific material ripped directly from the neutron star's crust, the rapid neutron capture process would starve. There would not be enough free neutrons concentrated in one place at one time to build the heaviest elements in the quantities we observe. The crust is not just a protective layer, it is the raw ore for the universe's most valuable treasures. So where do these heavy elements find their starting point? The entire rapid capture process needs a foundation, a seed. In the chaotic cloud of a neutron star collision, those seeds are often the most common of stellar metals, iron. An iron nucleus with its 26 protons is sturdy and abundant, the cosmic equivalent of a lump of clay waiting to be shaped. As this iron nucleus is swept into the neutron-rich tidal wave of ejecta, it is immediately caught in a blizzard of subatomic particles. It begins capturing neutrons at an astonishing rate, dozens of them in the span of a single heartbeat. This rapid, frantic assembly transforms that stable iron seed into something entirely new and wildly unstable. It becomes a super-heavy isotope, a bloated nucleus so saturated with neutrons that it is barely recognizable. Think of it like a sponge, absorbing so much water that it becomes heavy, misshapen, and ready to fall apart. This new, temporary nucleus exists far from what physicists call the Valley of Stability. It is an extreme, unbalanced form of matter that cannot last. To find its way back to stability, it must undergo a profound internal transformation. The excess neutrons inside its core begin to change one by one. In a process known as beta decay, a neutron literally turns into a proton, ejecting an electron in the process. Each time this happens, the element itself changes, because the number of protons defines an atom's very identity. So with every decay, the nucleus takes a step closer to a stable form. This step-by-step radioactive journey is how the universe transmutes a common seed of iron into a stable, precious atom of gold, or a rare earth element like neodymium. The R process is not a single act of creation, but a two-part cosmic drama, a frantic build-up followed by a slow, patient settling down that carves chaos into treasure. The brilliant, colorful firework of a kilonova is more than just a cosmic light show. It is a detailed birth certificate for new elements. How can we be so certain that gold and platinum are forged in these violent collisions? The proof is written in the light itself. As the cloud of freshly created, unstable elements expands, it is heated from within by its own radioactivity. The atoms are constantly decaying, and this process releases energy that makes the entire cloud of debris glow with an intense, evolving light. To read this story, astronomers use a powerful tool called a spectrograph. This instrument acts like a cosmic prism, splitting the light from a distant event into a full rainbow spectrum. But this rainbow is not smooth. It is etched with a unique pattern of dark and bright lines. Each chemical element, when heated, absorbs and emits light at very specific colors, creating a barcode that is exclusive to that element. This pattern is its spectroscopic fingerprint. When scientists trained their telescopes on the Kilonova of 2017 and broke down its light, they did not see the simple signatures of common elements like hydrogen or helium. Instead, the spectrum revealed the clear, unmistakable marks of heavyweights like cesium and tellurium. The presence of these elements, which can only be formed through the most extreme processes, allowed researchers to confidently infer the creation of even heavier treasures like gold and platinum in vast quantities. That single spectrum was the smoking gun, the direct observational proof that confirmed what theorists had suspected for decades. The light we saw was not merely a flash in the dark, it was the literal glow of cosmic alchemy, the radioactive shine of the universe's heaviest elements announcing their birth. So while both cosmic explosions are essential, they operate like specialized factories. A supernova is an immense industrial forge, a foundational event that manufactures the bulk materials of the universe. It produces enormous quantities of the elements that form the bedrock of rocky worlds, from the oxygen we breathe to the silicon in our soil and the iron at our planet's core. It builds the very substance of planets, but for the rarest, heaviest elements, its production line is inefficient and often unreliable. The Kilonova is different. It is a boutique workshop, a hyper-specialized event focused exclusively on the universe's most exclusive commodities. It takes the raw, neutron-rich material forged in the supernova's aftermath and transmutes it into the heaviest prizes. A single neutron star merger can generate hundreds of Earth masses of pure gold, along with vast quantities of platinum and the radioactive actinides like uranium and plutonium. This division of cosmic labor is what makes a planet like ours possible. Supernova provided the iron for our core and the calcium for our bones, but it was the Kilonovae, those rare and violent sprinklings of cosmic treasure, that laced our crust with precious metals and filled our planet's interior with the long-lived radioactive elements that keep its core molten and its geology dynamic. Without both types of cataclysm, the Earth would be a cold, static, and far less interesting world. That stardust, fresh from the Kilonova's forge, now faces an epic voyage. The explosion acts as a cosmic cannon, firing clouds of newly minted gold, platinum, and uranium outward at tremendous speeds. These heavy elements, once trapped in the ultra-dense heart of a collision, are now scattered into the vast emptiness between the stars. They mix and mingle with the thin gas and dust of the interstellar medium, a cosmic soup where the ingredients for new worlds are slowly simmering. This enriched material does not stay dispersed forever. Gravity, the great architect of the cosmos, begins to pull these scattered fragments together. Over millions of years, they accumulate into colossal structures known as giant molecular clouds, dark and cold nurseries where new stars are born. Our own solar system began its life inside one such cloud. When that cloud collapsed under its own weight, spinning into the protoplanetary disk that would become the Sun and its planets, it was not pristine. It was already seeded with the heavy elements from neutron star mergers that had exploded in our galactic neighborhood long before our Sun even ignited. This means the gold in a wedding ring is far more than a precious metal. It is a time capsule. Each atom is a physical piece of a catastrophic event that occurred billions of years in the past, a silent witness to a dance of destruction that made our very existence possible. But the universe rarely settles for a single solution. Beyond the cataclysmic mergers of neutron stars lies another, even more exotic cosmic powerhouse. Some neutron stars are born spinning with such ferocious energy that they amplify their magnetic fields to almost incomprehensible levels. These are the magnetars, the true magnetic monsters of the cosmos. A magnetar's magnetic field is not merely strong, it is 1,000 trillion times more powerful than the field that protects our own planet. If a magnetar were located as far away as the Moon, its magnetic influence would be strong enough to strip the information from every credit card on Earth. This unimaginable force does not leave the star untouched. The magnetar's crust, already under immense strain, is subjected to titanic stresses. This leads to violent starquakes, seismic events that release more energy in a fraction of a second than our Sun emits in 100,000 years. During these ruptures, the star's rigid surface cracks, and it can violently eject plumes of its own neutron-rich material out into space. Theorists suggest these magnetar-driven outflows, while smaller in scale than a full merger, create their own perfect pockets for the rapid neutron capture process. They provide another, more subtle pathway for forging heavy elements, sprinkling them into the galaxy one eruption at a time. This reveals a profound truth about cosmic creation. Neutron stars are not one-trick ponies. They are multifaceted engines of nucleosynthesis, each type contributing to the chemical richness of the cosmos in its own unique way. The study of magnetars adds a crucial layer of complexity, showing us that the universe builds its heaviest elements through a symphony of violent events, from the grand collisions of stellar corpses to the furious tantrums of its most magnetic inhabitants. To unlock the secrets of a neutron star collision, we must turn to the digital realm. We cannot recreate these cosmic cataclysms in any laboratory on Earth, so scientists build them inside some of the world's most powerful supercomputers. These are not simple animations, they are incredibly complex virtual universes governed by the fundamental laws of physics. The simulations must account for the bizarre distortions of spacetime predicted by Einstein's general relativity, the complex behavior of ultra-dense nuclear matter, the powerful influence of magnetic fields, and even the ghostly influence of neutrinos, particles that barely interact with anything. It is a computational challenge of the highest order. Running a single simulation can tie up a supercomputer for months, crunching quadrillions of calculations to model an event that lasts less than 2 seconds in real time. The result is a breathtakingly detailed digital reconstruction. We can watch from any angle as 2 neutron stars begin their final, fatal spiral. We can see the moment their surfaces touch and the violent tides of ultra-dense matter erupt into space. These virtual experiments allow researchers to measure precisely how much material gets flung outward, to predict its chemical composition, and to calculate the exact color and brightness of the resulting kilonova glow. This predictive power is what bridges theory and observation. When a real kilonova flashes in the distant universe, astronomers can compare its light to the simulated light curves from these models. It is like having a cosmic fingerprint on file, allowing us to confirm that what we are seeing is indeed the signature of heavy elements being born. Without these sophisticated digital forges, the brilliant light of a kilonova would remain a beautiful but ultimately indecipherable mystery. This internal planetary furnace, stoked by the decay of atoms forged in stellar collisions, is what keeps our world alive. Deep beneath your feet, radioactive elements like uranium and thorium are steadily breaking down, releasing a constant and gentle heat. This is not a destructive force but a creative one. This internal warmth is the engine that drives the slow, colossal churning of Earth's mantle. It powers the conveyor belt of plate tectonics, where continents drift, mountains rise, and ocean floors recycle. Without this geothermal heart, our planet would have cooled into a quiet, geologically static sphere long ago, much like Mars. A world without tectonic activity is a world without the vital recycling of minerals and nutrients. There would be no volcanoes to replenish the atmosphere with gases, no mountain building to create diverse habitats, and no carbon cycle to help regulate the global climate over eons. The very processes that make a planet dynamic and capable of sustaining a rich biosphere are fueled by this ancient, radioactive gift from the stars. But the influence of these heavy elements extends far beyond the planet's deep interior. Consider the unique role of gold. It is more than a symbol of wealth, it is a technological marvel. Its exceptional ability to conduct electricity without corroding makes it indispensable for the delicate circuitry in your phone and computer. Platinum is a powerful catalyst that enables chemical reactions essential for everything from cleaning car exhaust to manufacturing medicines and fertilizers. These are not just rare metals, they are elements with irreplaceable properties that underpin modern civilization. The cosmic debris from a long-ago kilonova did not just make our planet geologically active, it provided the very building blocks for advanced technology. Every time we mine a vein of gold or extract a sample of uranium, we are harvesting the legacy of a cataclysm that occurred billions of years before our sun was born. Our vibrant, complex world is a living monument to the violent, creative power of neutron star mergers. That single event in 2017 opened a new window onto the cosmos, but the view is about to expand into a breathtaking panorama. Our ability to witness these cosmic forges is undergoing a revolution, with a new generation of observatories set to scan the skies. Upgraded gravitational wave detectors like LIGO and Virgo are now more sensitive than ever, listening for the faintest ripples from colliding neutron stars. Soon they will be joined by the space-based LISA mission, a gravitational observatory that will open up an entirely new low-frequency band, allowing us to hear the universe's deepest rumbles. On the light side of the spectrum, ground-based telescopes like the Vera-C, Rubin Observatory will photograph the entire visible sky every few nights, creating a monumental, living movie of the cosmos. This powerful synergy means the next time neutron stars collide, we will not just see it, we will study it in unprecedented detail. Each new kilonova detection will be a treasure trove. By analyzing the gravitational wave signal, scientists can precisely weigh the neutron stars involved and measure their final, frantic orbits. The light from the explosion will then reveal the exact amount of material blasted into space, and through its spectroscopic fingerprint, the specific cocktail of elements forged in the blast. One event gives us a single data point, a solitary chapter in the story. But with dozens of mergers expected over the next decade, we will move from a single chapter to the entire book. We will learn how common these cataclysms truly are across cosmic time, and we will finally be able to calculate with statistical certainty what fraction of the gold in the universe was made in these violent mergers versus other exotic processes. This shift from a singular discovery to population studies will transform our understanding, turning the mysterious kilonova from a rare spectacle into a fundamental, measurable force in the chemical evolution of our galaxy. Yet for all we have learned, the cosmic forge still guards its deepest secrets. The brilliant flash of a kilonova confirms that neutron star collisions create heavy elements, but the precise recipe remains maddeningly unclear. What is the exact mix of gold, platinum, and other rare earths that emerges from the blast? The answer is not a simple list. It appears to depend critically on the specific nature of the colliding stars themselves. Picture two different celestial dances. In one, a pair of light, rapidly spinning neutron stars merge. In another, two heavier, slower corpses spiral together. The elemental output from these two events could be dramatically different. The masses and the spins of the merging stars act like master chefs adjusting the ingredients, altering the neutron flood and the subsequent decay, ultimately changing the final menu of elements produced. This variability means that not every kilonova creates the same distribution of cosmic treasure. Some might be rich in gold, while others overproduce platinum or rare earth elements vital for modern technology. This leads to an even more profound question. Are these mergers the universe's only heavy element factories? Some theorists point to the violent collapse of exceptionally massive, fast-spinning stars, known as collapsars, as another potential crucible. Certain rare types of supernova bubbling with magnetic fury might also contribute. The true picture of our cosmic origins may be more complex than a single, spectacular event. The path to solving these mysteries is written in the light of future kilonovae. Each new flash we detect is a cosmic laboratory report. By meticulously analyzing the color, brightness, and spectrum of that fading glow, astronomers can reverse engineer the explosion. They can deduce the masses of the colliding stars, the speed of the ejected material, and most importantly, the precise chemical composition of the newly forged atoms. Every solved mystery will fill in another blank on our cosmic periodic table, revealing not just where the elements were made, but how the specific conditions of each cataclysm shaped the very atoms that built our world. This relentless pursuit, driven by both powerful telescopes and immense supercomputers, continues to refine our origin story, reminding us that every piece of gold is not just a relic of a violent past, but a clue to a puzzle we are only now beginning to solve. These spectacular collisions are not just forges of matter, they are also cosmic particle accelerators of unbelievable power. The same catastrophic merger that creates gold can trigger a different kind of signal, one that travels across the universe at the speed of light. This is the short gamma-ray burst, a blink and you'll miss it flash of the highest energy radiation known to exist. For a fleeting second, a single gamma-ray burst can outshine every other source of gamma rays in the entire cosmos. For decades, their origin was one of astronomy's greatest enigmas. How could something so brief release more energy than our Sun will emit over its entire 10 billion-year lifetime? The leading theory points directly to the final moments of a neutron-star merger. As the two stellar corpses collide and collapse into a newborn black hole, the physics becomes almost unimaginable. The swirling, superheated debris forms a vast, thick disk around the black hole, a maelstrom of matter and energy. In this chaos, powerful magnetic fields can funnel a small fraction of the material into two narrow, opposing jets. These are not gentle streams, they are hypersonic beams of plasma accelerated to over 99.9% of the speed of light. It is the cosmic equivalent of focusing the fury of a supernova into a pair of laser-like rays. If one of those deadly, focused jets happens to be pointed directly at Earth, our satellites detect it as a short, brilliant flash of gamma rays. This explains why these bursts are so brief. The jet is like a lighthouse beam sweeping across the ocean. We only see the flash when it points in our direction. The kilonova we discussed earlier is actually the other half of this event. It is the glow from the slower, neutron-rich material that was ejected during the collision but was not caught in the ultra-fast jet. So a single neutron star merger ties together three of the most extreme phenomena in the universe. The collision creates ripples in spacetime we feel as gravitational waves. The birth of the black hole unleashes a focused jet we see as a gamma-ray burst. And the surrounding debris cloud forges heavy elements glowing as a kilonova. One cataclysm, three different cosmic messengers, all telling different parts of the same incredible story of creation and destruction. While supercomputers model the cosmic collision, the atomic details must be tested right here on Earth. The frantic neutron capture that forges gold happens far too quickly for us to observe directly in space, so scientists have found a way to recreate its essential physics in the laboratory. They use powerful machines called particle accelerators, which can hurl subatomic particles at nearly the speed of light. The goal is not to make a speck of gold, but to understand the behavior of the exotic, unstable atomic nuclei that are the crucial middlemen in this process. Inside these accelerators, researchers create beams of rare, neutron-rich isotopes that barely exist in nature. They then precisely measure how quickly these unstable nuclei capture additional neutrons and how they subsequently decay. These properties, things like neutron capture cross-sections and half-lives, are the fundamental nuclear data that dictate how the entire R process unfolds. Without these precise numbers, the magnificent supercomputer simulations of Kilonovae would be built on a foundation of guesswork. They would be like a complex recipe where you do not know the exact properties of your key ingredients. A new generation of facilities, like the Facility for Rare Isotope Beams, or FRIB, is pushing this frontier even further. FRIB is essentially a cosmic factory designed to produce and study the most exotic atomic nuclei that exist for only a fleeting moment. It brings the extreme nuclear conditions of a dying star into a controlled laboratory setting. This creates a vital feedback loop. Astronomers observe a kilonova and measure its light. Nuclear physicists then run experiments to determine the properties of the nuclei that must have been present to create that specific light signature. The modelers then update their simulations with this new, hard-won data. It is a close collaboration across disciplines, a partnership between those who look to the stars and those who probe the atom, all working in concert to finally decode the universe's most complex recipe for creation. Our galaxy's oldest stars act as cosmic time capsules, their atmospheres preserving the chemical makeup of the universe from billions of years ago. Astronomers who study these ancient suns are like stellar archaeologists, sifting through the light of these aging giants to take a census of the elements present in the galactic infancy. What they have found is truly startling. The signatures of heavy R-process elements like europium and gold are etched into the spectra of stars that formed when the Milky Way was just a toddler. This means these precious metals were already seeding the galaxy long before our sun was even a glimmer in a nebula. The presence of these heavy elements so early in cosmic history sends a clear and dramatic message. Neutron star mergers could not have been rare, slow-motion events that took eons to unfold. They must have been happening rapidly, lighting up the young universe with their kilonova flashes shortly after the very first generations of massive stars lived and died. This discovery places a tight constraint, a strict cosmic deadline, on the entire life cycle of binary neutron stars. It means these dense stellar remnants had to find each other, form a binary system, and spiral together in a merger within a few 100 million years at most. The universe was apparently in a hurry to forge its heaviest elements. This early appearance forces scientists to add up all the potential sources to see if the numbers actually work. They must perform a grand accounting exercise on a galactic scale, balancing the cosmic budget of elements. How much gold does a typical kilonova produce? How often do these mergers occur? Can their combined output, added to the contributions from magnetars and rare supernova, account for the total amount of heavy elements we see scattered throughout the galaxy, from the oldest stars to the newest planets? It is a monumental task of cosmic bookkeeping, ensuring that the sum of all creation matches the observed abundance of the atoms that build our world. This galactic enrichment process is a slow but relentless transformation of the cosmos itself. Picture a galaxy in its infancy, a vast, pristine cloud composed almost entirely of hydrogen and helium. The very first stars to ignite within this simple environment are titans, burning hot and fast before exploding as supernova. These initial blasts seed the void with the first heavy elements, a light sprinkle of oxygen, carbon, and iron. This is the start of a cosmic feedback loop that will govern the galaxy's entire future. With each new generation of stars, the available gas becomes less pure, slightly richer in what astronomers call metals, any element heavier than helium. This increasing metallicity is not a minor detail. It fundamentally changes the rules of star formation. Gas clouds with higher metal content can cool more efficiently, allowing them to fragment into smaller, more numerous clumps. This is why later generations of stars tend to be smaller and longer-lived than the first brilliant giants. The universe, over billions of years, shifts from creating fleeting, monstrous stars to fostering stable, sun-like stars around which rocky planets can coalesce. This is the grand narrative of chemical enrichment, the process by which galaxies grow up and become complex. Without it, our Milky Way would still be a dull, simple expanse of hydrogen, incapable of forming the diverse planetary systems that might harbor life. But where do neutron star mergers fit into this galactic life cycle? They are the specialists in this cosmic economy. While supernova provide the bulk raw materials, kilonovae inject the universe with a precise, critical set of heavy elements. These rare events are responsible for seeding the galaxy with the specific atoms needed for rocky planet formation, for driving geological activity, and for creating the elements that underpin complex technology. A galaxy without neutron star mergers would still have stars, but its planets would be geologically dead, its chemistry far simpler, and its potential for technological life severely diminished. The gold and uranium created in these collisions are not just cosmic luxuries, they are active ingredients that push a galaxy further along the path of complexity, enriching not just its substance but its very potential for the future. The detection of that single neutron star merger, known as GW170817, did far more than solve an element mystery. It flung open a new window on the cosmos, marking the true birth of a field called multi-messenger astronomy. For the first time, we did not just see the universe, we felt it. We combined the traditional story told by light with the physical shudder of gravitational waves, creating a complete, multi-sensory picture of a cataclysm billions of light years away. This was astronomy with depth perception. The future promises a view that is even more spectacular. Next-generation gravitational wave observatories, like the upcoming space-based LISA mission, will be so phenomenally sensitive that they could detect the spiraling dance of neutron stars from the very edge of the observable universe. We will no longer be limited to catching the occasional nearby merger. We will be tuning in to a constant cosmic chorus of collisions happening across the vastness of space and time. This changes everything. By cataloging thousands of these events, we will be able to probe the rate of neutron star mergers throughout cosmic history. We can ask fundamental questions. Were they more common in the wild, early universe? How did their rhythm of creation shape the chemical evolution of the very first galaxies? Each gravitational wave signal is a direct messenger from the event itself, carrying encrypted information about the masses and spins of the colliding stars. When we pair this with the light from the resulting kilonova, we get a full forensic report. The waves tell us what crashed, and the light reveals what was forged in the impact. Gravitational waves are so much more than just ripples in spacetime. They are our most direct guide to the universe's most energetic and creative factories, leading us back to the very forges that built the atoms of our world. These theoretical models push into a strange and uncharted territory of matter. The nuclei created in the Are process are so saturated with neutrons that they exist only for a fleeting instant in the fury of a kilonova. They are phantoms in the nuclear landscape, too unstable to be studied in any conventional lab, yet their properties hold the key to the entire cosmic recipe. How quickly do they capture another neutron? How do they decay? The answers dictate whether the final outcome of a collision is a mountain of gold or a surplus of platinum. To predict this, scientists must solve one of physics' most stubborn puzzles, the strong nuclear force. This is the immensely powerful glue that binds protons and neutrons together inside an atomic nucleus. While we know the force exists, mapping its behavior for every possible combination of particles is a monumental challenge, especially for these exotic, neutron-drenched nuclei. The rules change when a nucleus is overwhelmed with neutrons. The delicate balance of the strong force is tested to its absolute limit. Theorists are now mapping the so-called neutron drip line, the ultimate boundary of existence for matter. Beyond this line, a nucleus simply cannot hold another neutron. It would be like adding one more drop of water to a sponge that is already completely saturated. The extra neutron just drips right out. For most elements, the precise location of this drip line is a complete mystery. We simply do not know where the edge of nuclear stability lies. Filling in these blank spaces on the nuclear chart is like completing a map of a new continent. Without it, our simulations of the Are process are navigating blind. Every new data point, every theoretical advance in understanding the strong force, allows us to redraw this map with greater accuracy. This, in turn, lets us run more precise simulations of Kilonovae. we can input the newly calculated nuclear properties and watch as the virtual explosion produces a specific pattern of elemental abundances. We can then compare that virtual pattern to the real one we observe in the light of a distant kilonova. It is a slow, meticulous process of cross-checking theory against reality, gradually closing the gap between our nuclear models and the actual alchemy of the cosmos. This detective story of cosmic origins does more than just answer scientific questions. It forges a powerful connection between the universe and our daily lives. That smartphone in your pocket is a direct link to a cataclysm billions of years old. The gold in its circuitry, the platinum in its components, even the uranium used in certain medical treatments, all were born in the violent death throes of distant stars. These are not abstract concepts locked away in a lab. They are physical pieces of the cosmos that we hold in our hands. This narrative transforms the periodic table from a chart of abstract symbols into a dynamic history book, one that tells the epic story of stellar life and death. When we share the tale of how a neutron star collision creates the atoms that make up our world, we are doing more than just relaying facts. We are inviting everyone to see the universe not as a distant, impersonal void, but as a place of profound creativity, one that is intimately connected to our own existence. The detection of the 2017 kilonova was a perfect example of science in its most thrilling form. It was not a slow, incremental addition to human knowledge, but a sudden, dramatic leap. In a single observation, decades of theory were confirmed, and our understanding of the cosmos was instantly and permanently rewritten. This is the real excitement of science, the recognition that our maps of reality are always provisional, always ready to be expanded by the next great discovery. It demonstrates that fundamental research, the pure pursuit of understanding how the universe works, is not an isolated academic exercise. It is the very process that reveals our own deepest origins, showing us that we are not just living in the universe, but that we are truly made from it. This cosmic origin story for our most precious metals casts a new light on humanity's future in space. The same gold and platinum forged in ancient Kilonovae are the very resources we now look to mine from asteroids and other celestial bodies. This is no longer just a question of engineering or economics, but of profound cosmic perspective. Every atom of platinum we might one day extract from a space rock carries the legacy of a stellar cataclysm that occurred billions of years ago. It is not merely a resource waiting to be collected. It is a chapter in an epic narrative of universal creation. This knowledge invites us to shift our thinking from simple exploitation to a deeper form of stewardship. How do we responsibly utilize materials that have traveled across the galaxy and through eons of time to reach us? The ethics of space mining are suddenly intertwined with the history of the cosmos itself. It suggests a framework where we approach these resources not as owners, but as temporary custodians of a shared cosmic inheritance. Recognizing the incredible journey behind each element encourages a mindset of respect and long-term responsibility, a consideration that must guide our steps as we become an interplanetary species. The future of resource utilization in space may well be written not just in corporate charters, but in the very star stuff we seek to gather. Unraveling the mystery of the universe's heaviest elements demands a symphony of scientific minds. This is not a puzzle that any one expert can solve alone. The astrophysicist who models the cataclysmic merger of two neutron stars relies entirely on the nuclear physicist working in an underground laboratory. That experimentalist, in turn, is measuring the properties of exotic atomic nuclei based on clues provided by the astronomer who observed the fading glow of a kilonova. Each specialist holds one piece of the map. The gravitational wave hunter who first senses the ripple in spacetime immediately alerts the teams operating giant telescopes across the globe and in orbit, turning our entire planet into a single, coordinated instrument aimed at the cosmic disturbance. This convergence is the beating heart of modern science. The biggest questions about our origins have become so complex that they shatter the old boundaries between disciplines. The success of multi-messenger astronomy, where we both see and hear the universe, is a powerful testament to what humanity can achieve when we collaborate on a global scale. It is a shared endeavor that pushes the entire frontier of knowledge forward, proving that the secrets of the cosmos are only revealed when we listen to each other as intently as we listen to the stars. From the cataclysmic collision of two dead stars emerges the very material that makes our world rich and diverse. These cosmic powerhouses, neutron stars, serve as the universe's ultimate alchemists. They take the simple ashes of long-dead suns and, through the violent, rapid neutron-capture process, transmute them into the heaviest elements. We have journeyed from a decades-old theoretical puzzle to the direct, awe-inspiring observation of a kilonova, a brilliant confirmation that we are literally made from the debris of the most extreme events in the cosmos. This is not a metaphor. The atoms that construct our bodies and our world were forged in a stellar cataclysm that occurred billions of years before our solar system even began to form. This profound story connects the almost incomprehensible scale of colliding stars to the tangible reality you experience every single day. The next time you feel the weight of a piece of jewelry or simply consider the solid ground beneath your feet, remember the incredible journey it represents. That gold was born in a frantic 2-second neutron blizzard. The uranium that heats our planet's core is the lingering warmth from its own radioactive birth in a cosmic explosion. The universe is not a distant, separate entity. It is a part of us all, woven into the very fabric of our existence. If you found this journey from stellar death to planetary life as fascinating as we did, make sure to subscribe for more deep dives into the mysteries of the cosmos. Let us know in the comments which element's origin story you would like to explore next.